present Tanvi Dinkar. Tanvi is a PhD student at Télécom Paris, Insitut Polytechnique de Paris, and a Marie Curie Fellow at ANIMATAS. Her PhD studies the representation of disfluencies for spoken language understanding. Her research interests include spoken language understanding, psycholinguistics, communicative strategies, and the discrepancies between the way people speak versus the way people write. Tanvi has a very interesting background. She has 2 masters from the University of Edinburgh, one in linguistics and one in speech and language processing, and she completed an undergraduate degree in journalism and literature. I personally love the fact that what made her pursue a PhD is realizing that dialogue systems are not robust to people's disfluencies while working at Nuance, now Microsoft. Today, Tanvi is going to talk about how to use social Today, Tanvi is going to talk about representations of fillers and discourse markers in spoken language understanding and from a psycholinguistic perspective. So Tanvi is experiencing some Wi-Fi issues. So we think we have all covered if something goes wrong. So Tanvi, don't worry at all about that. And the floor is yours. I'm going to stop sharing my screen so that you can share yours.
Maybe it's better if one of us share the video so that if Tanvi has any problem with that.
I think Tanvi is experiencing a problem right now, right? Not the only one. Okay. So maybe since we have everything under control as usual.
Sorry, did I get frozen?
Yes, but it's fine. Miguel, we shared the screen from his computer because it doesn't make a...
And I will also try to switch the network. So I'd like to thank Talking Robotics for inviting me to present my thesis work, which is titled The Representations of Disfluencies in Spoken Language Understanding, a Psycholinguistic Approach. So I will unpack the terms in this thesis as in the upcoming slides. So first, an introduction to disfluencies. People rarely speak in the same manner that they write, and disfluencies are an inherent characteristic of spontaneous speech. Formally, disfluencies may be defined as interruptions in the regular flow of speech. You might pause silently, you might repeat what you said previously, and you might also interrupt yourself to correct something you said previously. These are all considered disfluencies, which is the opposite of what is considered fluent. Now, here is an example of a disfluent utterance, which is very natural to spontaneous speech. The way it would be transcribed is as follows, where the disfluencies are marked in bold. While I'm working, I don't get a chance to read the paper a lot, and I don't watch TV as much really either, because my free time is I do like to do other stuff with it. Now let's look at the same utterance with the disfluencies removed. While I'm working, I don't get the chance to read the paper a lot, and I don't watch TV as much really either, because my free time is I do other stuff with it. So my thesis focuses on disfluencies called non-sentence elements, which are speech events that are characteristic of spontaneous speech. So there may be words such as well, or sounds such as and they're not considered to add to the final lexical message, but are very illuminating on a conversational level. If we look at the comic to the right, we can see that the professor is having a typical conversation with the student and asking, so the writing isn't going well. And the student is saying, and I think we can tell by the student's use of disfluencies that the writing probably is not going rather well, and it sets up the tone for the rest of the comic. The student was using what is called a filler, which is a disfluency filling a pause in an utterance or a conversation, such as or in English, and my thesis principally focuses on fillers. Now, despite the rich linguistic literature on the informativeness of disfluencies, in spoken language understanding and spoken dialogue systems, Fillers and other disfluencies are typically considered as noise and removed from the input utterance. Now, I will explain a little bit more about spoken language understanding and spoken dialogue systems in the upcoming slides as I explain the problem statement, disfluencies in spoken language understanding. So first, what is spoken language understanding? It's not one defined application. It combines speech processing, natural language processing by leveraging technologies from machine learning and artificial intelligence. So there is a broad context of spoken language understanding where you might, for example, analyze acoustic characteristics of speech to annotate, automatically infer things like engagement of the speaker or what kind of emotions the speaker was feeling. So that's more of a broad context of spoken language understanding tasks. But there's also a more narrow focus of spoken language understanding, and that's as it's used for spoken dialogue systems and HRI, where the focus is on task-oriented dialogue. The goal here is to reduce the input utterance to a semantic frame using intent classification and slot detection. Let's take an example where maybe the robot is at a train station and the human wants help in buying a ticket. So the human might say, a train ticket to Berlin, I mean to Paris. So here the intent of the utterance would be to book train tickets, and the slot here would be Paris. And this would be the semantic, reducing the input to the semantic frame. Now you might be wondering that, hey, maybe in this context it makes sense to remove disfluencies, so shouldn't we just remove disfluencies? But this is not always the case, as natural language is really complicated, and oftentimes disfluencies are very informative about not only the speaker's underlying intentions, but the listener's interpretation of the speaker's underlying intentions. So let's take an example. When a speaker says an utterance, they convey in the incoming message their communicative intents, difficulties in formulation, certainty in what they say, etc. So A here says, can I borrow that book? And B says, all right. Now A might interpret that B is hesitating a little bit to lend the book compared to if B said, all right, immediately. So here A in turn needs to assess the utterance and decode this information. Maybe A responds to B's hesitation by saying, oh, I promise I'll return it by Monday, to reassure B that she will return the book quickly. Let's look at an example that could be more tailored to spoken language understanding, as we know in spoken dialogue systems. So A says, I'd like to make a reservation tonight at the nearest Indian restaurant. And the robot says, sure, for how many people? A says, for 2 people. And the robot says, okay, should I book a reservation at Maharaja at 7? And A says, all right. Perhaps A at this moment realized that she was thinking of a different Indian restaurant, or that her friend actually doesn't like this restaurant. Now, a typical response might be, I have made a reservation at Maharaja for 2 people at 7. But wouldn't it be nice if the robot could respond the way the listener might comprehend the speaker's use of disfluent speech and say, I made a reservation at Maharaja at 7, but I'm available if you'd like to discuss further. Now, quickly, I'd like to talk about disfluencies in text-to-speech and HRI, which are predominantly from a speaker's perspective. So we have systems like Google Duplex, which uses disfluencies to enhance the naturalness of conversation. And Google Duplex is an AI system for accomplishing real-world tasks over the phone. So I'm going to play out an example now.
How can I help you?
Hello?
Hello, what's up, man?
Hey, I wanted to know what are your hours for today?
10 a.m. to 6:30 p.m.
Okay, got it. Thank you for your time.
No problem, sir. Bye.
Now remember here, the person that is calling in is TTS, and it fooled the human into thinking that they were speaking to another human by the agent's use of disfluencies, so saying, I'd like to know what are your hours. Similarly, disfluencies have been used from a speaker's perspective as a communicative strategy to hold the floor during turn taking. And you might have seen in some Wizard of Oz studies that disfluencies might be used as a time-buying measure, while in the background, the agent or the robot, it's being decided what should be the agent or the robot's next move. So now, to give you a little psycholinguistic background on the listener's perspective of disfluencies. So the speaker may or may not consciously encode meanings into their speech, so they may control or not control their use of disfluencies. So there are studies that focus on the comprehension of disfluent speech by the listener. Disfluencies are ubiquitous to spontaneous speech, so the comprehension system or the listener must have developed strategies in order to process them. So I would like to read out a quote by Corley, who says, "It is hard to determine the reason that a speaker is disfluent, especially if the investigation is carried out after the fact from a corpus of recorded speech." Now, I think this is applicable to several data sets collected for the purpose of spoken language understanding research, where you might have a large data set of speech that is collected, and then you might ask annotators after that to listen to the speech and annotate the corpus for high-level attributes such as engagement or emotions, etc. And indeed, it's found that the listener comprehension is affected by disfluencies. So some interesting examples is the listener might expect the speaker to shift topics if they hear a disfluency. They might relax the listener's expectations when hearing an unpredictable word, and it might even bias listeners to new reference introduced into the discourse rather than ones already that have been introduced. So for this reason, we focus on the listener's comprehension of disfluencies. Now, getting a little bit into the works that I said I will present today. The first work is a joint work by Pierre Colombo, me, Mathieu Lebeau, and Chloé Clavel, which we presented at EMNLP. We have the general research question of whether fillers affect the comprehension of the listener in spoken language understanding. And we have two objectives. We'd like to assess empirically whether fillers play an important role in spoken language or whether they should be removed as noise. And we'd like to assess whether fillers play a role in the listener's perception of the speaker's expressed confidence. Now, this is inspired by psycholinguistic work by Brennan and Williams. So we'd like to experimentally validate these objectives without handcrafting features in an unsupervised manner. And we'd like to efficiently represent and study the informativeness of fillers using state-of-the-art language models. Before I get a little bit more into an intuitive meaning behind language models, I'd also like to talk about the data set. So as you can see here also at the bottom, I've given the title of the paper, which we presented at EMNLP. So we choose the POM dataset, which is a dataset of 1,000 American English monologue movie review videos. The interesting thing about this dataset is speakers voluntarily and naturally recorded themselves giving a movie review. There was no concerns about whether this would be used in a dataset. They were simply uploading a video of themselves telling you either to watch or not watch a movie. Then annotators had to watch these videos and annotate these videos for high-level attributes. So they were asked questions like, how confident was the speaker? And asked to annotate on a Likert scale of 1 to 7, with 1 being not confident and 7 being very confident. They were even asked to annotate things like how persuasive was the speaker using the same kind of Likert scale. We choose this dataset because there's annotations of fillers and confidence available, and the filler count is exceptionally high here. It's 4% of the words in the dataset. For comparison, a commonly used dataset of human-human dialogues, the switchport dataset, is about 1.6% of fillers. The inter-annotator agreement for confidence also is high here, showing that annotators seem to agree about the confidence of the speaker, and there were 3 annotators per video. We also chose this dataset because the annotators were not particularly asked to pay attention to the speaker's use of fillers, and this is a dataset of monologues. So the speaker is conscious that there is an unseen listener, and they are conscious that their video is going to be seen by other people, but there are no dialogue-related disfluencies interrupting the speaker as such. So here's an example of the videos of the POM dataset, and we use the transcripts of this dataset.
Hi, my name is Jordan, and I'm going to be reviewing Master and Commander, The Far Side of the World. Well, this movie, it has Russell Crowe in it. This movie came out a few years ago, and it is awesome. It is basically about a captain of a ship a long, long time ago, back in the days of Napoleon and things like that.
Now, if you were wondering, Jordan was rated as rather confident by the annotators. So now to get into language modeling, because we want to study the informativeness of fillers using state-of-the-art language models. So here is an intuitive interpretation. How would you model the probability of the sentence? It would be how likely is this sentence to occur in natural language? So we have here two sequences of words, German beer drinkers versus German beer eaters. Now both of these sequences are grammatically correct, but the probability of seeing the sequence German beer drinkers is higher than the probability of seeing the word German beer eaters in natural language. So you'd want a language model that will give us good approximations of sequences or sentences that are likely to occur in natural language. Now we use a language modeling task of pre-trained BERT, fine-tuned on the same mass language modeling objective. Now, to briefly talk about the mass language modeling objective, that means that the training involves masking some percentage of the input tokens at random and then predicting those mass tokens. Now, when we talk about pre-trained language models fine-tuned on the same mass language modeling objective, the idea behind pre-training is that skills that you might learn for one task might intuitively be applicable to another task. So let's say that you learned how to build a table. When you learned how to build a table, you might learn how to use certain tools. You might learn how to cut certain materials. So then when you have to move on to the new task of building chairs for the table, some of those skills might be transferable and you're not starting from level 0. So that's the same idea behind pre-training and fine-tuning models. A pre-trained model is training a model with one task to help it form parameters that can be used in other tasks. And fine-tuning is using the model parameters of tasks that have been learned before to initialize the model parameter of new tasks. In our case, we have a pre-trained language model that is pre-trained on written text that we fine-tune using the same mass language modeling objective on our spoken language BOM dataset. So first, we'd like to assess whether fillers play an important role in spoken language. We'd like to empirically assess this in an unsupervised way. So as I said before, we use a language modeling task using BERT with the same mass language modeling objective to fine-tune on the POM dataset. For each experiment, we have a different token representation strategy and a pre-processing strategy. Now, what does that mean? Let's say the raw input transcripts where the fillers are marked in red is things that you usually wouldn't find funny. So step 1 is the pre-processing strategies. PS1, we have fillers removed, as they would be in spoken language understanding, during both training and inference. And PS1, we have fillers kept, both during training and inference. So here's PS1 with the fillers removed, things that you usually wouldn't find funny. And PS3 is the same as the raw input. Then we have different token representation strategies. Some examples of these are TR1, where there's no special treatment done to the fillers. This will try to make BERT learn using its a priori knowledge or representations of fillers. And TR2 is a special token will be attributed to each filler and and this aims at trying to force BERT to learn a new representation that will distinguish each filler. So here's an example of the token representation strategies. You can see in TR1, there's no special treatment done to the filler. And in TR2, you can see that there's an individual representation for each filler. Now, in terms of the results, we optionally fine-tune BERT for each pre-processing strategy and token representation strategy using the mass language modeling procedure. Now, for results, we find that fillers do not need to be removed as noise in a spoken language modeling task, because PS3 consistently gave us the lowest perplexity, which is fillers kept both during training and inference is the best pre-processing strategy. So for a spoken language modeling task, fillers can be leveraged to reduce the uncertainty of BERT. Now, this was found using the evaluation of perplexity. This is not expected because intuitively you might think that when you remove when you remove fillers, the sentences are shorter or that they're simplified and that the perplexity might be reduced. We also found that the first token representation strategy is the best, which means it's better to keep the existing representation BERT has of fillers. It's interesting because BERT already has a representation of fillers in written text. They already exist. And we also found that BERT was unable to distinguish between the two fillers and despite linguistic literature even recently to suggest otherwise. So there's already a representation of fillers. They can be used to reduce the uncertainty of the language model, but at the same time, there are some drawbacks that the language model is unable to distinguish between the two uses of fillers. The second objective is to assess whether fillers play the role in the listener's perception of the speaker's expressed confidence. So here we have a downstream confidence prediction task to show the informativeness of fillers. What we do is we add a multi-layer perceptron on top of BERT to fine-tune it on a confidence prediction task. We fixed token representation 1 as the strategy, and we experiment with the same pre-processing strategies as before. We can optionally first fine-tune the pre-trained model using the mass language model objective on the spoken language data set of fillers, and then again fine-tune on the confidence prediction task. We evaluate confidence using the mean squared error loss. In terms of the results, again, we find that PS3 consistently outperforms the other pre-processing strategies. That is, when we keep fillers in training and inference, both with and without using the mass language modeling fine-tuning objective. Thus, fillers can be a discriminative feature in confidence prediction. The takeaway here is that fillers do not need to be removed as noise. When we have a fine-tuning task of the listener's perception of the speaker's expressed confidence, fillers can be a discriminative feature. Now, we validated this on a spontaneous speech data set. Many times when this phenomena was found in linguistic literature, it was in slightly more limited contexts, such as QA contexts, and maybe also in smaller data sets in laboratory settings. Now, this is speakers speaking naturally and uninterrupted, voluntarily giving movie reviews, where listeners are then later asked to evaluate the speaker's confidence without being asked particularly to pay attention to the speaker's use of fillers. And we presented an unsupervised way of studying the informativeness of fillers. Now, you might be wondering, where did these, if BERT is pre-trained on written language, where did these initial representations of fillers come from? But fillers also occur many times in written text as well, usually when the author is deliberately trying to either show some uncertainty of the speaker or used as a conversational device also. So here I have an example from Harry Potter, where Gilderoy Lockhart says, "Hello, who are you?" And Ron says, "Ron Weasley." Gilderoy Lockhart says, "Really? And who am I?" Ron says, "Lockhart's memory charm backfired. He hasn't got a clue who he is." So in this case, it begs the question, when fillers are written in text, do they have a different sense from when they are used in spoken or spontaneous speech? Because often listeners do not necessarily pay attention to a speaker's use of fillers unless they're misused or overused in the wrong contexts. Now for RQ2, I'd like to present some preliminary results we have from a journal paper that is under review, where we study what is the role of disfluencies in alignment between interlocutors. So I have the same example where A says, "Can I borrow that book?" and B says, "I'm all right." Let's say A responds, "Thanks, can I borrow your notes too?" and doesn't really pick up on B's hesitation. So there's a joint responsibility of interlocutors that any contribution to the conversation is mutually understood. And here we can tell that A is not understanding B's hesitation or reluctance to lend the book. If A says, "Oh, I promise I'll return it by Monday," we can see that they are aligned in their intentions. And a dialogue is successful when there's alignment between the interlocutors at different linguistic levels. So the question here is, how do disfluencies interact holistically with the rest of the message when considering alignment between interlocutors? We use the Just Think dataset, the Dialogue and Actions corpus, which is a collaborative learning activity where there might be immediate performance goals, so interlocutors often work together to achieve success in a task, and there might be learning goals, so interlocutors might be assessed on how much they learned from the activity using pre- and post-tests. A problem is that there's a lack of automatic tools to analyze verbal interactions in a collaborative learning activity, and qualitative analysis require extensive manual annotation. And I've given at the bottom a link to the preprint of our paper that was co-authored by Uthku Norman. Now, I first want to refer you to the amazing works of Jaberia Nasir and Uthku Norman, who designed and collected the Just Think dataset. I will briefly talk about the setup of the Justing dataset. So basically, this QT robot acts as the CEO of a gold mining company and tells the children that they need to work together to connect all the gold mines by building railways. Now, these railways each have a cost to connect to each of the gold mines, and they are told to find a minimal cost solution. They are allowed to submit their solution as many times as they want, and the QT robot will either encourage them, if they have not found a minimal cost solution, to continue, or will tell them whether they have found a minimal cost solution. We chose to focus on this data set, and we focus more on the verbal interactions of the children in this data set. So I'll also refer you to the previous week's Talking Robotics presentation by Javeria Nasir, where she focuses more on the acoustic data to study productive engagement. Now, we think this is a really interesting data set because the children have two different views of the task. One is an abstract view where the person in the abstract view can see the cost of connecting the gold mines, and the person in the abstract view has to instruct the person in the visual view to connect the gold mines. So basically, they have to figure out how each other is referring to this map, and then they have to instruct each other and follow each other's actions to lead to teamwork and alignment. So building on that, this is a situated activity, and the communication thus has an additional dependence on the immediate environment, and this entails interlocutors referring to the physical environment. An appropriate action can be taken when interlocutors understand the other ways of referring to the environment. So here A says, what about Mount Davos to Mount St. Gallen? And B says, what if we could do it? A says, what about Mount Davos to Mount Gallen? And then B says, Mount Davos. So now B can take an appropriate action because he understood the mount that, or the gold mine rather, each of these mounts are gold mines. B understood the gold mine that A was referring to, and now they might continuously refer to that gold mine as Mount Davos. Now, referring expressions that are fixed become shared or established among the interlocutors. So now maybe Mount Davos is part of the shared vocabulary, and they will continuously use Mount Davos to refer to that particular gold mine. So we automatically annotate two levels of alignment in the situated activity: the use of expressions related to the situated activity and the follow-up actions of such expressions. We automatically do this using state-of-the-art alignment models. Now, first, when we study the use of the expressions, we'd like to study the link between fillers and the establishment of shared expressions. And we'd also like to study the link between the discourse marker O and the follow-up actions of the automatically inferred instructions. Now, I'm not going to get too much into details of the methodology because of lack of time, but we basically use a Mann-Whitney U-test to study the distribution of the filler times with our automatically annotated establishment times and the discourse marker O times with the automatically inferred follow-up actions. And then we use Cliff's delta to estimate the effect size. Now, just quickly to show you an example transcript with our automatically inferred actions and automatically inferred instructions with matching or mismatched actions. So you can see here B is adding Basel to Bern. So they're connecting two nodes or two gold mines, Basel and Bern. And you can see that A had previously instructed B to add Basel to some other node. So we account for partial matching as well. And you can see it's a match in pink. And then A says, yeah, and then go to Mount Zurich. So then the automatically inferred instruction here is add Zurich to another node. Again, a partial match. And then B adds Basel to Zurich. So again, it's a matched action with the instruction. Now the takeaways, quickly the takeaways of this work are: one, that fillers tend to occur when listeners establish the speaker's referring expression into the shared vocabulary space. Now we think that's because when the speaker is giving instructions, they might be in the abstract view. So they might be able to see very clearly which gold mines they want connected and which costs. However, the listeners in the role of clarification need to say, oh, did you mean this mountain to this mountain or Mount Davos to Mount Gallen? So the listeners are using this as a clarification tool, basically the use of fillers. We also found that the discourse marker O tends to occur when the instructions given by the speaker are not followed by the listener. So when we infer automatically the instructions of the speaker and they're not followed with actions from the listener, then we see also the discourse marker O occurring. And we also found that the distributions of O and this phenomena of mismatched instructions to actions overlap for better performing teams. So maybe better performing teams are using this discourse marker O to inform each other of potential miscommunication. So now, a few conclusions on future work. Disfluencies are an inherent characteristic of spontaneous speech. I hope my presentation has shown that. And they can affect the listener comprehension and listener-speaker dynamic in many ways. We found in an unsupervised way that fillers are not nice and need not be removed in a spoken language modeling task, as the addition of fillers can be used to reduce the uncertainty of a language model. We also found that fillers can be used as a discriminative feature in a downstream task of predicting the listener's perception of the speaker's expressed confidence. Using weakly supervised models and moving to the listener-speaker dynamic, we automatically infer the alignment of expressions and follow-up actions in a situated activity to find that listeners tend to use fillers before establishing expressions into the shared vocabulary space, and that discourse markers O tend to occur when instructions were not followed by the same action, and this occurs more for better performing teams. In future work, we will concentrate on the role of disfluencies in both the clarification and confusion of the perception of communicative intents. Lastly, I'd like to thank all my collaborators and my supervisor, without whom this work would not be possible. And I'd like to draw people's attentions to the picture on the top left, where me and Utku are aligning on the intentions of winning the video game. Okay, thank you.
Thank you very much, Tanvi. Actually, at some point, I forgot this was a video, and it seemed like, and I wanted to ask questions as you were speaking.
Yeah, I didn't want to interrupt. Sorry, I could have presented midway, but then I thought, okay, let's not interrupt the flow. Yeah.
So, do you have any questions from the audience?
Just a question. I'm not entirely sure if this is, I think, more pertaining to the future work as well. When you mentioned that you could actually identify that certain disfluencies could lead to certain specific follow-ups, like O meant that, oh, the speaker B, for example, was taken by surprise, and that led to like an understanding and basically a shift in conversation like that. Do you think it would also be possible then to identify disfluencies for sentiment analysis or any other more generic, like to understand, essentially? Like if someone was very negative in a conversation and just like, just certain disfluencies, do you feel like there's more in that area for identifying special disfluencies for specific follow-ups?
Yeah, that's a very good question. So there was a PhD student in 2017 that studied the role of disfluencies in stance marking. So stance is the subjective attitude towards something. And we also, in our EMNLP paper, we didn't just do the downstream task of confidence prediction, we also did a downstream task of sentiment analysis, because there is both linguistic literature to support that fillers have a role in confidence prediction and in sentiment analysis. It's linked to both, and found that fillers are a discriminative feature in stance marking and sentiment analysis. So in fact, our future annotation campaign will also be about how confused is the listener by the use of disfluencies, because sometimes you might have certain expressions like I think, I believe, and you might have these kind of expressions that sort of soften a statement. So a very factual statement is the sun rises in the east, but maybe you'd say something like I think the sun rises in the east. And, you know, you might start, the more you use these kind of uncertainty expressions, the more you might start confusing the listener into thinking that they are expressing some sort of, you are expressing some sort of sentiment. So in fact, yes, our future annotation campaign will be testing this, and it's a really good question.
Thank you so much.
I kind of have a follow-up question on that, because I was thinking about the fact that you said at the beginning and throughout your presentation that these fillers and these fluencies carry meaning, and they carry intentions, they carry beliefs, and perhaps goals as well, right? Even in the examples that you showed, I think illustrates that. And we have this impression that language models have some limitations and cannot help us. Like, if, for example, in the design of agents and dialogue systems, it can help us to a certain point. But from your presentation, I get this idea that BERT can also have, or BERT or another language model already takes into account those disfluencies, and you showed that they are not noise, in the sense that they also carry meaning. What's your take? So it's not a question here, like a specific question here, but I'm just saying, I'm just thinking that if BERT takes that into account, can we do more with the language models?
Yeah, it's a really good question. So right now, as I pointed out, that there is an existing representation of fillers that BERT contains that exists somewhere in the written corpus. And the claim right now is that you can fine-tune language models to learn aspects of spontaneous speech. So there's works by professors like Mary Ostendorf, etc., that show that you can automatically learn not just things like fillers, or disfluencies, but also things like prosodic features, right? Because disfluencies are very linked to prosody. So you can also learn things like prosodic features, etc., and characteristics of spontaneous speech using BERT. But I think that there are certainly limitations there. So this is an upcoming work, but we, for example, found that BERT, for example, cannot distinguish between the two fillers and a. Right? And linguistic studies have shown that they are used in very different ways. So I think that you can learn characteristic of spontaneous speech up until a certain point. And right now, since the focus is so much on this semantic interpretation or the lexical, so reducing the input utterance into exactly what was said and not how it was said, I think soon in the coming years, as we focus a little bit more on these dialogue related aspects, then we will focus a little bit more on improving the representations of spontaneous speech. Because right now, the focus is still very much on collapsing the input utterance into what was said in essence. So I don't know if that answers your question, but yeah.
It adds food for thought. It was just a thought. It is not a question, a direct question. It's just something that I think it's interesting to think about, and it's an outcome of your research, which is very important from my perspective.
Yes, and I will also say that I think most people who are working on disfluencies are still working on disfluencies very much with the context of removing them or improving disfluency detection for the purpose of removing them. So there is like kind of just a few niche labs in the world that are focusing on you know, how informative they are, inspired by all the linguistic literature about disfluencies.
It's just because I've never seen them from that perspective, and when you exposed them as carrying more meaning, I find that very exciting, because you use when building dialogue systems, I look at fillers and disfluencies as a way of switching the floor or perhaps changing topics, which I do not know if it's a good strategy or not. But I haven't thought about them as structures that carry more things about the speaker.
Well,
Okay.
even right now, your use of fillers informed me that you were still speaking while you were formulating your thought process. So I know that, okay, there's still an incoming message. I, as the listener, could interpret that. So, yeah.
Okay, so I think we have a question in the chat. I'm not sure if you want to jump in, Joari. I can read it if you want.
Yeah, I guess you can go ahead and read it. I have a bit of noise in the background.
Okay, so I'll read your question. So Joari says, thank you, Tanvi, for this very interesting presentation. Do you think these fluencies and the intent they may carry, especially the outcomes you presented, changes between adults and kids? Secondly, I was wondering that with these outcomes that you have, what might your biggest takeaway be for robotics researchers?
So thank you for the question. It is a very, very big question. So there are studies that show that kids can also comprehend disfluent speech the way that adults comprehend disfluent speech, but generally children might be more disfluent, as well as, you know, there's like a lot of contextual things about this. It might be chalked down to speaker style. It might be chalked down to whether you're a second language speaker of a language. So there are many individual things that might determine whether you're disfluent. So me and Utku try to address this in our paper by focusing on disfluencies. So you would have seen that we transcribed a representative subset of the just-think dataset. And what we did is we just focused on the non-sentence elements that I mentioned, so people saying and not maybe more complicated disfluencies that require a lot of different kind of annotations. And we also focused very specifically on expressions that were related to the situated environment. So I think that's a first takeaway for robotics researchers, that if you want to study dialogue, there are you know, still some very interesting nuances to be found about the dialogue by just focusing in on the situated environment. Yeah, I guess that's also probably a bigger takeaway for robotics researchers rather than spoken language understanding, because in spoken language understanding, I would see a much bigger takeaway is that fillers can be used to reduce the perplexity in language models for a spoken language understanding task, and also successfully in downstream tasks. But I think for robotics researchers itself, I would say that the way to study dialogues with all its messiness, all its disfluencies or situated dialogues is to focus on expressions that are very specific to the task at hand, and then also focus maybe on these conversation level disfluencies. Yeah.
I think we have a question from Glenda. I'm sorry if I missed that, but your square moved around and I only see it right.
Yeah, so thank you a lot, Tanvi, for the talk. It was quite interesting. I'm not so familiar with your topic, so my question is also related a bit to where I come from myself. So I work in human-robot interaction, social robotics, and I'm related maybe to what Ioana is saying, and also this last question here about the contribution and application in a sense. I'm just wondering, because for human-robot interaction, there are also a lot of aspects of building rapport, making the interaction fluent and natural. And I was just thinking, in your presentation, there was a lot of focus on this fluency in terms of understanding and comprehension. But we also see, for example, with robots that, you know, these kind of social mechanism of mirroring and copying kind of can establish rapport. And language might be one of the domains too. And I wonder if you see it in your data, if these fluencies might also be adapted as a way to kind of established report? Because sometimes if people want to get along with people, they use the same words or the same phrasings. And I'm wondering if people also pick up this, but I'm not sure if that's possible to see in the data sets, but is it something that you are exploring, whether they can also be used outside of comprehension, but for a report establishment?
Yes, so right now, I focus a little bit more on the listener's comprehension because I do think that in HRI, there is more of a focus on using filler disfluencies as a communicative strategy and as a repo strategy. So, for example, I played out that clip by Google Duplex where to enhance the naturalness of the conversation, the TTS system had disfluencies to fool sort of the human into thinking that they were talking to another human. Or I also cited some other papers where fillers and other disfluencies were successfully used to hold the turn, the speaker turn, when the robot was interacting with the human. I think that was by researchers from KTH. So I can also share my slides in the Slack for anyone who wants some of those references. And lastly, I also, I think said that, there's Wizard of Oz studies where disfluencies are used as a time buying measure, while, maybe in the background, someone is deciding what should be the next steps of the robot. So I think that there is already some really interesting work that is done on the speaker's use of disfluencies as a sort of communicative strategy, which is why I chose to focus on listener comprehension. But I think that there's definitely a lot of work to be done in both areas. And in the work with UTKU, we don't necessarily only focus just on the listener comprehension, but we try to focus on just the distributions of disfluencies in terms of the alignment of expressions, right? The speaker volunteers an expression into the shared vocabulary, and then the listener will accept that expression by repeating the expression, and then it becomes part of the shared vocabulary, right? And we simply look at where the distribution of fillers falls in this alignment process. So that's not necessarily actually only the listener comprehension in that sense.
Is there any other question? So I guess if it's not, there's not, I think we can finish this session and move this discussion to the Slack channel. First of all, thank you very much for your presentation and for this discussion.
Thank you.
I really liked it. I've learned a lot, and I hope other people too. And I would like to share my my slides again, so that I will present the next speaker. Okay. So in our next session, which will be, I'm sorry. I'm very, very sorry. Let me stop sharing and we'll do this again. I do this every time. Okay, so let's present the next session. And so our next speaker is going to be Ellen Björling. I hope I pronounced it correctly. And she's from the University of Washington, and this is going to be the last talk of this season. So we are going to finish the spring season, and we hope to come back strong in the fall with new speakers, new topics, and I hope and I hope that you can join us